Every circuit that you have seen so far has been an example of combinational logic. And by combinational logic, I mean that the output of the circuit is dependent only on the input to the circuit. So this is a very simple circuit that you're looking at right here, and I can see that the output will be a 1 if I have key A as a 1. So if I flip down key A and not, this is a little not gate, and not B, I get a 1, right? A and not B, I get a 1. That's the only time that this circuit is going to output a 1. If I try every other possible combination, the output stays 0. But again, if I flip down A and not B, I get the output of a 1. So combinational logic means that the output is only dependent on the present input, not what the previous input was. Interesting. Now we're going to look at another kind of circuit. This is a sequential logic circuit. You have not seen this before, and I'm going to run through it, and you will be amazed. So here I have both switches open. I have a 0, 0 input, and the output, which I've labeled Q, is off. And I'm just going to go through this, and I think you'll see something a little bit different. So I'm going to flip down key B here, and you can notice the light comes on, and now I'm going to open it, and the light stays on. Wait a minute. Last time I had both switches open, the light was off. Let me try that with A again. I'll flip down A, the light goes off, and I will open the circuit, and the light stays off. So sometimes when I have an input of 0, 0, the light is off. Sometimes when I have an input of 0, 0, the light is on. It's almost as if the circuit remembered what the previous input was. Let me do this one more time. It's so amazing. I'll flip down key A, the light goes off. Now I open the circuit, the light stays off. So here I have a 0, 0 input, the light's off. Now I'm going to flip down key B, open it again. Now I have a 0, 0 input and the light is on. I have created 1 bit of memory here. Sometimes 0, 0 represents the light being on. Sometimes it represents the lights being off. The 0, 0 state in this particular circuit is called the memory state. I can either set the memory state, I can either set the bit to 1, open it, it stays as a 1. I can set it to 0, open it, it stays at a 0. This is sequential logic. The output not only depends on the present input, but on the past input. Interesting. We're going to be working with sequential logic quite a bit. And if you actually look at the circuit itself, the way it's constructed, you can see that the output of these NOR gates come back around as inputs. So it's really weird. And you can trace through this if you like and try to figure out what's going on. But the important thing to notice is that the outputs become inputs. They come back around and are inputs. So the output, I'll say it one more time, is so amazing. The output of this circuit not only depends on the current input, but on what the previous input was. And in a minute, I'm going to have you play around with this circuit and really try to figure out how it works. Let's take a look at one more example of a sequential logic circuit. Now here I've added a couple of AND gates to the beginning. Then these circuits are going to get pretty complicated pretty quickly. So we really don't have to worry too much about the specifics of what's going on, but you do have to understand what the output will be based on the input. So I'm just going to run through this. So here I've labeled this key reset and this one set. And if I set this circuit, in other words, if I flip this switch on and back off, you notice Q turned on. And now I have a 0, 0 input, right? Both set and reset are zeros. 0, 0 is called a memory state. If I click reset on and off, I have now reset this particular circuit. So you can see Q is off and it stays off. Remember, 0, 0 is memory state. So it remembered what the previous state was. So I'll set the circuit. I'm back in memory state. I'll reset it. I'm back in memory state. And if I turn enable off, so this circuit is not enabled, clicking reset and set do not do anything. So this circuit only operates or only changes in state if you click enable. And one more thing that I want to point out is that notice the state that I have not been in is if I try to reset and set at the same time. And now when I click enable, yeah, it goes crazy. You get what they call a race condition. And if you think about it, it makes sense. You can't set and reset something at the same time. The circuit goes nuts. So let me just reset the thing there. Okay, so I'm back in memory state. So again, I can set my circuit, I can reset my circuit, and I can only change the state if enable is on. One other thing that I've connected here is I've connected another output and I've labeled it Q prime. That's another way of saying not Q. And notice Q and not Q are always in opposite states, hence the name Q and not Q. Not Q is always the opposite of Q. Again, I can reset and set, and Q and not Q are always in opposite states. Below, I have the schematic diagram of what this gated SR latch is going to look like. If you use one in multisim, you don't have to build it from discrete gates. You can look at this diagram, and this, you really should understand how to read this. S stands for set, R for reset, EN for enable. So obviously if I send a 1 to set, it'll make Q a 1, it'll turn Q on. If I send reset A1 or RA1, it'll turn Q off. And of course I have my enable switch, and of course they're both 0 zeros, S and R both 0 zeros, that's my memory state. Now I know you're thinking, well, what are these set and resets on the top and bottom? We're not going to get into that right now, but we will shortly. So you're going to now do a little lab where you're going to play around with this gated SR latch and just get comfortable with what the outputs are based on the inputs.